Okay, so I'd just like to welcome everybody to this presentation on behalf of the ASG committee. My name is Gary Raftery. I lecture in research in timber engineering here at the University of Auckland, and this evening we have got a very interesting presentation lined up by Dr. Marjan Popovski. And Marjan has come from Vancouver in Canada, where he's a principal scientist at Advanced Building Systems in FP Innovations. Marjan has a wealth of experience in seismic knowledge on timber structures, so he's going to talk to us about the advancements and challenges that have been encountered in North America over recent times. Marjan is sponsored for his trip here to the University of Auckland for a week, thanks to a fellowship that's given by the department, and he's also close colleagues with Pierre Quinville, our prof of timber engineering here. So the floor is yours, Marjan.
Thank you so much, Gary. Good evening, everybody, and it's really a pleasure to be here with you today at this relatively late hour, so really appreciate your time, and I hope you learn something new. I hope you come home with a little bit more knowledge than when you came in. So I'm a principal scientist in FP Innovations in Vancouver, in Canada. FP Innovations is Canada's Forest Products Research Institute. So it's a Canadian public-private partnership that includes federal government, provincial governments, and industry members. You know, Canada has states called provinces. We have about 450 employees in 3 main laboratories across the country, the main ones being in Vancouver, Montreal, and Quebec City. And our research budget is about $65 million a year. We do research in the entire chain of related to wood, from wood harvesting to wood transport, to engineer wood product, processing wood, engineer wood products, and all the way to how those products are used in the buildings, basically on the top of the food chain where my department is. So as Gary mentioned in the introduction, I work in the building systems area, so lots of experience in seismic performance of timber buildings and innovative systems that use timber. So first of all, why do we use wood in buildings? Wood is one of the longest standing building materials which homes built over 10,000 years ago. It is the only renewable construction material that really contributes to the removal of greenhouse gases, and it has a low environmental footprint because it requires less energy to be processed and produced, much less than other building materials such as steel or concrete. It has also what engineers are interested in, high strength to weight ratio. And no better example than this one. This is, for younger generations, probably you're going to see this for the first time. This is so-called Mosquito aircraft. It was the fastest airplane during the Second World War, and it was used by the Allies with great precision. It was one of the aircraft that actually won the war. It was made completely out of wood, except the engine, the landing gear, and parts of the cockpit. So that tells you that wood can be used anywhere because of its capabilities to have strength with respect to its weight. And there are lots of applications. Wood can be durable and can be long-lasting. Examples of that are everywhere. On the left, you can see Norwegian stave churches, which have been around for more than 800 years, or the House Bethlehem in Switzerland, which is probably the same time. So these are one of the oldest buildings in Europe, wood buildings in Europe, and they've stayed the weather and everything that's been thrown at them. So the problem is that wood can be durable. The problems that we have today is that designs are not adequate to make the wood stay as it is and be durable. The wood has proven seismic performance. For example, this Horyuji temple in Japan, built in 670 AD, it survived 46 earthquakes with magnitude 7 or higher. So that's a lot. 46 magnitude 7 and higher earthquakes and virtually no damage. They can be tall. as this pagoda in China, which is 67 meters tall and standing for more than 1,000 years. And they can be really tall. So what you are looking at is the tallest wood structure on the planet. It's a radio tower in Poland, built in 1934, just before the Second World War. So basically can spy on the Nazi Germany at the time and get the communications from the future enemy. So in 1934, we were able to build structures that are 120 meters high. But as I'll show later, the times came when we basically went quite in the other direction. Wood buildings can be also large. And this is a wood building. It's one block in one dimension, almost 2 blocks in the longitudinal direction. It's a bit ugly on the outside, and you'll say, oh, this is not a wood building, but actually it is a wood building, 44 meters high, 9 stories. It's Butler Square building in Minneapolis. But when you go in the inside, you see the real beauty. So it's a beautiful open space, heavy timber building with a combination of offices, restaurants, and gathering spaces. It's a beautiful space to be in. It's really enjoyed by a number of professionals who have their offices there. And just to show you that buildings like this, as big, have been built 100 years ago. And speaking about tall buildings, which will be one of the main topic of my talk, wood was not doing that bad in the history. So, for example, this is in the US. At the turn of the 20th century, late 19th and turn of the 20th century, we had that 9-story timber building in Minneapolis, 44 meters high. The biggest concrete skyscraper was the one in Cincinnati with 64 meters. And the Chicago steel home insurance 12-story steel building with a height of 42 meters. So wood was not doing that bad at the time. Actually, we were right there somewhere. Similar story in Canada. We have a wood building on the left side, plenty of them in Vancouver, in Montreal, and all Toronto and other big Canadian cities with heights of 30 meters, even 40 meters. And on the right, you have the Dominion building in Vancouver, built in 1910, with 13-story steel frame building. When built in 1910, this was the highest building in the British Empire. So wood was somewhere close to the highest building in the British Empire. Well, then the Dark Ages came, at least Dark Ages for wood. So this rich history of wood use in tall buildings was halted during the second decade of the 20th century. And there were many reasons for that. Fire performance concerns, frequent fires in major cities, although many people say now they were suspicious. Of course, we have no evidence. Wide availability of structural steel as a material, rapid development of reinforced concrete technology at the turn of the century, and last one, the rise of architectural modernism that didn't include wood. So we blame the architects a little bit for this. So because of all of this, suddenly from having timber buildings 40 and 50 meters high, we went down in just number of years, restricted to low-rise construction up to 4 stories, and this lasted for almost a century, almost until early 1990s. And then in the early 1990s, there's a renewed interest in wood, which basically also there are several reasons for that. First of all, changes in the building codes. That as you probably know, most of you are engineers here, the building codes changed from prescriptive design to objective-based design. That helped wood a lot. Then we had government support and legislations to basically promote wood in use in a number of buildings. Of course, development of mass timber products such as parallel strand lumber, laminated strand lumber, cross-laminated timber, and so forth. Innovative manufacturing technologies such as CNC numerically controlled machines, and development of innovative connections. And finally, the society came to a stage where there was a search for greener construction materials. So all of this together, again, like 100 years ago, there was lots of reasons that went against wood. All of these reasons now suddenly went for wood. And that resulted in a real renaissance of use of wood buildings that we are seeing today. Cross-laminated timber was one of the main items that really get the spotlight back on the mass timber buildings. For your information, in Canada, there are 3 manufacturers, one in BC, one in Quebec, and one in Ontario. There's a strong interest among designers and architects. There's a strong support from federal and provincial governments, especially in British Columbia and Quebec. And there are considerable research and development activities going on to basically implement not just cross-laminated timber, but also other products in buildings. Then another buzzword came in 2011, tall wood. This was the report that was produced by Michael Green Architects and Equilibrium Consulting, architectural and engineering firm from Vancouver. And in 2011, they produced a report where they studied a system so-called FFTT, or Finding Forest Through the Trees, which is an unusual name. But what they proved as a concept is that, yes, wood can work in 20-story buildings, in 30-story buildings, or even in 40-story buildings. So that's 2011, and since then we see really explosion of what we call tall wood buildings. Not tall in terms of steel and concrete, tall in terms of wood, which means 10, 12-ish and in that range. So the first tall building in Canada was the Wood Innovation and Design Center in Prince George in central British Columbia. It's a 29-meter building built in 2014. So when built, it was the tallest contemporary wood building in North America. And it was, from structural point perspective, it was the first building that used CLT in balloon-type construction. Because cross-laminated timber, it was first produced in Europe, and of course first used in Europe, it was always used as a platform type of construction. So basically you have your wall, then you have your floor, and then you have the next wall and the next floor, and so forth. So you basically, you develop a platform on which you build the next floor, the next story. This is the first building basically in Canada that used balloon technology for the walls, which means the walls are going all the way from the bottom to the top of the building. So you can see here the lateral system was taken by these elevator shafts and stairwells, balloon type walls, while the gravity system is all around by using glue-lam columns and beams. Then in 2013, NRCan, which is a ministry in the federal government, Natural Resources Canada, announced request for proposals for tall wood demonstration buildings. And there were over 25 proposals, and out of those 25, 3 were selected. The 13-story CLT building in Quebec City by name of Origin, 18-story building at UBC in Vancouver by name Brock Commons, and 12-story post-tension building in Ottawa. The last one is still on hold. It went into some problems, but we hope that it will be built soon. But the other 2 are completed. So the 18-story Brock Commons, the rendering of the building you see on the left, and the 13-story Origin building in Quebec you see on the right. So let's see about the Brock Commons building. It's basically a hybrid building, 53 meters high, 18 stories. The lateral system consists of 2 concrete cores, each of them basically housing the elevators, or should I say the lifts here, and the stairwells. And so those 2 cores are basically taking the lateral loads, the earthquake and wind loads. The gravity system is basically 2-way point-supported CLT floors, and loads are transferred directly to glue-lam and PLCL columns. So what was innovative about this building was the floor system. As you know, if you transfer the floor above to if you transfer the load from the floor above through the column, and then then the floor sees that load, basically you have huge compression perpendicular to grain forces on the floor. So to avoid that, in this case, the designers came with an innovative solution that transfers the load from the column above to the column underneath directly through a steel tube. So this is a cross-section of that steel tube. So you can see right away here the load from this column is transferred through the steel tube to the column underneath. So floors were basically independent. And they were lying, the floor panels were just all around these columns. So basically, we have point-supported CLT floors. In most cases, until this building, CLT was always supported on walls. So you have a long line of support where you put the CLT panels, and they mostly work in one direction, like one directional, say, reinforced concrete slabs. In this case, the CLT floors, they worked in two directions. So you see here how the floor panels are installed on the top of the columns. So each floor panel spanned 2 bays. So this is 1 bay, 2 bay. So this is one panel, and this is the next panel. So each panel basically supported on 6 columns, which means, because there is no continual support at the edges of the panels, neither in this direction, neither in this direction. So basically, the CLT floor panels, they have to basically work in 2 directions. So to help the designer, of course, CLT has never been used in 2 directions, so we had to do some testing. So this is a picture from the testing in the lab in FP Innovation. So basically, we were very instrumental in the design and research behind the design that went into the building. So we tested a total of 18 different floors, some of them with big openings here, meter by meter openings for pipes and other stuff. Some of them without openings, some of them with different configuration, different thickness of panels and so forth. Because the designers, they have several designs in mind, but they just wanted, and of course they've built their finite element models, but they just wanted a proof that really their model work and basically which panel to choose for the building. So here you can see the floor during the testing. You can nicely see really how the floor works in 2 directions. So there's bending in this direction, but there's also bending in this direction as well. And to be honest, I was really surprised by the results that we got. For example, before the tests, I would have said that the strength of the column of the floor without this big hole, meter by meter hole, and without and with the hole would be significantly different. But at the end, the strength comes within 5%, which means the CLT, through that interlocking mechanism, defined a way how to transfer the load around the holes. And I was, to be honest, very, very surprised of that. This is the failure mode that we obtained. So it's a combination of rolling shear and tension perpendicular to grain at both ends. So of course, the bending moment in the middle is the highest. So you have failure at this point. But also what was interesting here is when we basically unloaded the floor, it bounced back up right away. So it was another interesting finding that we've never seen in CLT so far. Engineers were also very happy. It proved their design, so they were very eager, and they implemented the design in the building. Since it is the highest wood building in the world, of course, we had to think about the fire protection strategy. And for this building, we had 3-fold fire protection strategy. First one was not significant exposure of wood, which means most of the wood was covered with 1 or 2 layers of gypsum, depending on where the wood was used. Building was fully sprinklered, and we had also 30 minutes on-site backup water supply, a 20,000 liter water tank that basically was always available in case of there is no water. So those are the 3 things that really 3 lines of defense in terms of fire. So you can see here in blue are 1-hour rating walls, and in red, so there are 2 hours. So floors, they had to be 2-hour fire rated, while for the walls, 1 hour was okay. This is the installation of the facade of the building. So at the beginning, the contractor who basically put the building together, of course, it was new to them. They received some training, but it had some problems at the beginning. But where they reached the 18th story, they were said, wow, what a nice way to build a building. And this is installation of the facade panel. And the beauty of this system was it was built in 9.5 weeks. So 18 stories in 9.5 weeks completed. And you have the view from the top of the building. By the way, the top of the building is a common area. This is a student building, by the way, student residence. So we experimented with students first, see how it goes. And I have to stay because I see some students here probably. One of the reasons they wanted to cover the wood with gypsum was also abuse. So it was not all fire-related concerns. They also had other concerns because they will be first-year students, and you know the first-year students, at least in Canada, they graduate from drinking, say, one of the items on their list. Anyway, long story short, it's a beautiful view. As you can see from the top, UBC is located in a beautiful area in Vancouver. And when we took this picture, by the way, from the top, the elevators were not working. So it was quite a workout. So the second building is the Origin building in Quebec. Again, this building used the balloon-type shear walls. As you can see, the shear walls are going all the way from the foundation to the top of the building. And it is the highest building with 13 stories right now that uses this type of technique. Here is the plan of the building. So in red, you have the position of the shear walls. So 7 different types of shear walls. And they also use some shear keys here that I'll just explain in a minute. Then the next project, again in Montreal, in Quebec, was Arbora building complex, which is still the largest mass timber residential complex in North America. It consists of 3 8-story buildings with total of 434 residential units. Again, this complex used balloon walls for lateral loads and the CLT floors for gravity loads, and of course columns to transfer the gravity loads. So to help this movement into the tall wood buildings, FP Innovations has been leader along working with universities in Canada. So we developed a technical guide for design and construction of tall wood buildings in 2014. We also developed a guide for province of Quebec for mass timber construction up to 12 stories. And actually based on that, because in Canada, the building code is on the national level, so the national building code is the model code that covers the construction for the entire country, but the provinces are those, the governing legislation comes from the provinces. So basically the provinces adopt the Canadian model code, but they can also change it. So province of Quebec, for example, they decided based on the report that we prepared for them, they decided that basically they can lift the limitation for stories up to 12. So right now in Quebec you can build up to 12 stories, while in other parts of Canada you have to provide alternative solution. Ontario, province of Ontario is to follow suit. So just a few months ago, they developed the Ontario Tall Wood Building Reference. And this is all to help designers basically, giving them valuable information, how to design, how to analyze these buildings, and how to approach the entire problem. Significant amount of research went in Canada regarding mass timber construction, structural performance, connection performance, seismic performance, fire, durability, serviceability, acoustic environment, and even health effects of wood in buildings. So FP Innovations was fully involved, and we provide a holistic approach to our research. So basically what you see there, we were part of everything. And this is how we see that how the things should be done, because I'm structural engineer myself, so I always lean towards structural areas. So, okay, we can come up with a very good structural solution, but if that solution is not good for fire, we haven't done anything. Or it's not good for acoustics, or it's not good for something else. So really that holistic approach of teams working together to develop new solutions, that really paid well, and I think we are on the right path as an organization as well. And basically, many universities started following this path as well, at least in Canada. So, since we are here in New Zealand, in the earthquake country, not many people know that Canada also has high seismic zones. And they're mostly located in the western part of the country, in the north, and also in the eastern part of the country, in Quebec especially. So, the city with the highest design acceleration is Victoria. Victoria is about 400,000 people. Design acceleration 1.3 G, so it's quite high. Vancouver, which is 2.5 million, design acceleration 0.86 G. And cities like, so these are kind of the high seismic zones. Then Montreal and Quebec City are about moderate seismic zone, 0.6 and close to 0.5 G respectively. So lots of major cities in Canada, which probably not many of you knew, that they are in moderate to high seismic zone, especially the west coast. By the way, the return period of these big subduction earthquakes on the west coast is about 350 years, and the last earthquake we had is about 1720. So we are there. It could come any day. So, speaking of seismic, we did lots of testing on cross-laminated timber and other mass timber walls to find out basically how they perform, what are the main parameters that influence the seismic performance of cross-laminated timber walls. So we tested walls with different configurations, aspect ratios, different heights, with openings, without openings, with various types of fasteners and so forth. We'll not go into details, but we found out what we needed basically, that some fasteners, they perform poor, and by looking at this hysteresis loop, you can definitely tell this, these screws that were used at 45 degrees to connect the wall to the CLT underneath, they are not performing well during an earthquake. While if you use regular nails and or similar screws, they can perform very well, and you can get very developed hysteresis loops, lots of energy dissipation in the system. And in mass timber, everything happens in the connections. So you have to find a good connection to have a good system performance. Then we moved into three-dimensional experimental testing. This is a two-story house that was tested at FP Innovations. Basically, we wanted to see, again, the two-directional motion, because testing one wall is one thing, testing a three-dimensional thing is something else. We learned how basically perpendicular walls behave, what is the, how the stories are connected together, and basically do they influence one another. Again, what we got here is that the response was combination of rocking and sliding deformations. The walls with openings had higher in-plane deformations. Main deformations were in the joints between the panels, and on purpose we put joints between the panels so when they rock, basically they dissipate energy. And what was interesting is that we achieved actually up to 3.2% of story drift at the bottom story. And the most important is that the structural integrity was not compromised even at failure, or what we called failure at 3.5%, 3.2% story drift. So again, just a few information. Here is basically determining the types of deformation that CLT or mass timber building will have. So you have global rotation of the building, you have rocking of every panel, then you have sliding, and then you have in-plane shear and bending deformation and so forth. Then we went further and said, okay, we now have component tests, we have data. Let's now determine the R factors, or which are in New Zealand here, K mu factors. Those are the factors that are used in seismic design that they reduce the elastic base shear. So you have the elastic base shear and it's divided by these factors. So basically you design the building for a reduced shear because of the ductility of the building. So those ductility factors, we used a building that we also were part of that project. This is in 2009, a 6-story stick frame building tested at the largest shake table in the world in Miki, Japan, just outside Kobe. So this was a test where we basically tested the possibility of going from 4 stories stick frame to 6-story stick frame. So this test was basically a pinnacle of that research. It was led by Colorado State University. But we used the same building now, and we redesigned it analytically, numerically, we redesigned it as a CLT building. So we used the same floor plan, but instead of 2x4 walls, we used CLT walls, and based on, of course, component tests that we have. And then we developed analytical models, numerical models for 6-story, 10-story, and 15-story buildings, and so forth. So it's a long analytical process. A total of 60 different buildings were analyzed using the Sapwood program. And the results basically, they show, these are the fragility curves, so some of you are familiar with. Basically, these curves, they show what is the probability of failure on y-axis, or cumulative distribution function, nothing else than probability on non-failure, versus the maximum story drift, which is the deflection at the story level. So if you want, for example, depending on what performance level somebody wants, say we want performance level of 0.8, which means we have 20% probability of failure, but 80% probability on non-failure. And for this desired maximum interstory drift, say in this case 2.5%, then basically this is your performance point. So all these lines, which represent a series of dynamic analysis on a single building designed with certain R factor, or in your case would be with certain K mu factor. So your performance point is here, which means that the buildings with RD 1.5, 2, and 2.5 were okay. But the building underneath, which is the green one, which 3.0, that factor is too much. The building will have a higher level of collapse. So by basically designing the building the way you want, you can come up with the R factor that is suitable for that building. Same fragility curves, or a 10-story building. As you can see here, as the building goes higher, the probability of failure goes lower, actually. So coming back to balloon mass timber walls, they're very practical and efficient option for seismic force resisting systems, but there are no codified, there are no design methods everywhere in the world. So we initiated a research project to quantify the seismic performance and design of these walls. And of course, they've been used in the buildings that I've showed you in Canada. So engineers, the designers, they're really craving for some information. So we developed a testing program to help them. We tested different types of walls. But here you can see on the left one, balloon wall with just hold downs at both ends. Basically the hold downs are just taking the uplift loads. Then the entire wall was cut in half here and connected with connectors between the walls. And then also some coupled walls with stiff connectors along the height. Here are some close-ups. So you can see the close-up of the hold down at the bottom, a regular hold down with steel plates and screws, nothing fancy. So this is one configuration of wall. This is the second configuration, where basically the wall is split in two and connected with regular screws and steel plates in the middle. And the third configuration, basically we wanted, again, you have two walls here. So the walls is split in the middle, but then it's joined by these thick steel plates. So one of the problems in balloon construction is, of course, you have to go all the way up with your wall. So that's 13 stories, say in this case in Quebec. But the CLT panels, they come 3 meters wide from production. You cannot have a wider panel for now. So 3 meters by 40 meters, that's a huge aspect ratio. So you need really wider walls, which means you have to connect 2 or 3 CLT walls together. And you have to find a system that basically from 3 separate walls will join them into one performance-wise. So this was one idea that we came up with, and basically it worked. It worked well. Here are some results from load displacement curves from the walls with hold downs only. Here is the wall with hold downs and those inserted thick steel plates. As you can see, behavior was almost similar. So we achieved what we wanted basically. From one wall and 2 walls connected with something to have similar performance. The wall which was cut in the middle and connected with screws, of course, as expected, had a lower stiffness, but also higher deformability than the wall that was not cut in half. Then that building that I showed you in the Tallwood report, FFTT, we also had a research project to basically help that one become from a concept to a more usable solution. The basic behind that concept is that you have these balloon walls in the core of the building. So this is all wood core, mass timber core. But you also, so this is the core. You also have steel beams in both directions that are inserted in the wood core. So whenever the building in any direction starts to respond during an earthquake, you basically have plastic hinges that are developing in this area. The contact of the steel and the wood core So basically you have more or less steel failure mechanism of a weak beam, but also you're developing crushing during that time, crushing above and below in the core. So you have to design for both. This is again the system. Again, the core, around the core is the gravity load system. And again, the steel beams with the core CLT or any mass timber element. So the design was strong beam, weak column. And we tested quite extensively. This is a collaboration with UBC, with University of British Columbia, just next door to us. And we found, of course, excellent dissipating property, but also we developed some procedures that basically how you have to, how much you have to insert the steel into the mass timber panel, so to avoid basically rolling shear failure in the panels. And then again, almost a 4-year PhD here with numerical analysis, a huge amount of numerical analysis to determine the performance of this type of building and to determine the R factor, or in your case, KMU factor. And basically we come up with a factor of 5, which is really high for Canadian codes. It's one of the highest, actually. The steel moment frames and steel shear walls have R factor of 5 in Canada. Then a little bit more innovative. Those who are in steel know that better. There are different types of steel moment frames. They are highly ductile steel moment frames. They are probably expensive, but also they have steel frames with lower ductility. And those are cheaper solutions for steel. So we said, okay, what if we have a cheaper solution for steel and then you insert CLT panels in some of the base of the steel frame, and then you connect it with connectors. So we did lots of study, another PhD thesis here with UBC, basically studying and optimizing this solution. How it should be the gap, what should be the properties of each connector, where the connections should be located. Just a few items that we discovered. Which base should be basically paneled with CLT, which should not be. So there's lots of combinations of that one can play with. And we found out also, again, a lot of numerical analysis went in. These all curves are analysis, every curve is analysis of one building under a series of earthquakes. And we developed basically, again, the R factor for this type of system. I'm mentioning this R factor or KMU factor in your case here because all of these systems are right now not in the code. So the work like this really helps tomorrow to codify the system so it's all accepted by engineers and in practice. Wind performance is another performance that, as you all know, tall mass steel buildings are much lighter than concrete buildings or steel buildings. And they're more flexible by nature. So frequent exposure to wind-induced vibrations can really cause occupant discomfort. So in tall wood buildings, there's certain height up until really the seismic performance governs the design and the response. And depending on the system, that height could be 18, 20, or 25 stories. If you go higher, then winds start to govern the response. So really now your headache will come from the wind side. So, and to basically find out about how tall wood buildings perform due to wind loads, every tall wood building that was built in Canada is instrumented, and we followed it. We're finding lots of interesting results, how the buildings perform during some windstorms we have already. And there's a collaborative research going on this topic between UBC, Okanagan, the Western University, and FP Innovations. And we are basically trying to develop performance-based wind engineering framework. Like we have performance-based earthquake engineering, we're trying to develop performance-based wind engineering. One of the building concept that we studied in this case was so-called SOM building concept. SOM stands for Skidmore, Owing, and Merrill. This is a respected company from US. And they basically came up with this concept of up to 40-story building that is a combination, hybrid building, a combination of mass timber and concrete. So we took that their idea basically, and we said, okay, we're going to go with a 30-story building, story height of 3.4 buildings, and lots of details. I have no time, of course, here to explain. We designed the connections and everything according to the concept that was given to us. Then we had a scaled model that was tested at the wind tunnel testing boundary layer facility in London, Ontario, and also at the laboratory for Windy Dome at the Western University. They have one of the best, if not the best, facilities for this kind in the world. So out of this, we learned a lot, basically, how the tall buildings perform, how the pressure changes on a tall wood building. And out of this project, we want to get basically to develop a performance criteria that will tomorrow be codified for tall wood buildings. This is the first research of its type in the world, by the way. Then finally to the next level, which is resilient buildings. And you here in New Zealand know very well about this. Our friends in Christchurch, they found out the hard way, unfortunately, that life safety alone is not a good enough criterion for designing buildings from earthquakes. Yes, it's good, you have the life safety, but then you end up with having huge economic losses. So there is a really need for resilient, or what we call low damage structural systems that can reduce the damage while offering the same, or if not a higher level of safety to the occupants. And there are several types of systems that have been developed. One of them in Auckland that I had a chance to understand and see this week, developed by Professor Pierre Corneville, slip friction joints. Here I'm going to talk about post-tension controlled rocking systems, developed originally at the University of Canterbury in Christchurch, and then basically developed in different mass timber wall and beam and column systems. FP Innovations has purchased the licensing right for this system for Canada and the United States. And currently we are doing lots of research in this area. Although our colleagues from Christchurch, they've doing testing on this system for almost 7-8 years now, and they have lots of in-depth information. Most of that information is on LVL, so we wanted to basically see what will be the system performance with cross-laminated timber made of Canadian species and also Canadian products. Because this system, because of the post-tensioning effect, the material properties, they have significant effect on the system performance. So if something performed well with New Zealand LVL, not necessarily will perform well with the Canadian CLT. The system, probably you know it very well. You have post-tensioning cables. In this case, it's a wall system. So you have post-tensioning cables in the middle of the walls, and those walls are rocking. So the post-tensioning basically provides recentering after the earthquake. And between the walls or in some other places, you either provide UFPs, U-shaped flexural plates, or other energy dissipators to basically help with the energy dissipation. So these are tests in our lab in Vancouver as we speak, taken just a few days before I came here. We are trying to get the performance of single walls. Also, you can see here there are lots of axial dissipators that are connected to the walls. So you have UFPs between the walls, but there's lots of axial dissipators, which means just steel rods that will yield in tension and compression. The resiliency is really taking over most of the research in North America at this point. There's a huge push. We are also part of a big project, mainly US. Plenty of, a great number of universities here, from Colorado School of Mines to Colorado State University, University of Washington, Washington State University, Lehigh, Nevada, and so forth. So we have FP Innovations, ourselves there, and a few other design companies. So what we are working on is to develop basically resilience-based seismic design methodology for tall wood buildings. And the pinnacle of this project, there are componental tests going on right now at many of these universities, including ourselves. But the pinnacle of this project will be a shaking table test that will be done at the University of San Diego shaking table in probably 2019. So before doing a 10-story building, of course, it was nice to see what will be the performance of building with just a couple stories. So a series of tests were conducted at the same shake table in San Diego on a 2-story press lump system. Here are the details of the system. Basically, you can see the walls going all the way to the second floor, UFP, U-shaped flexural plates attached between the walls to help with the energy dissipation when the walls rock. And you have the post-tensioning cables here on the outside to be visible just for simplicity. And I can show you a video from the test. So the findings after the test, and actually we did quite a high number of tests, was 0 damage. The system performed really as designed. There was literally no damage. And we designed this system so that the walls can be taken out. So basically there's a hole in the diaphragm at both levels, so the wall can be taken out and replaced by another wall, just slot in another wall, and you can do another test. Take the walls out, put new ones in, do a testing. So we were experimenting with different walls, different connections, and so forth to find out. Even some designers that came up with innovative walls, they also jumped in. They said, oh, can we test this for 5K? We put new walls? Yeah, please do. So it is an interesting project. And again, as I said, we're expecting to have a 10-story building in more than a year from now. Other projects in the US, there's a large project that I'm also part of. We're trying to develop the seismic performance factors. Again, those are factors, famous factors for CLT construction to be implemented in the loading code in the US. So again, lots of tests from US CLT in wall applications, connection tests, and so forth. And we are at year 5 of this project, and hopefully we're going to finish this year, and then we're going to propose the system for acceptance in the US codes. Speaking of post-tensioning and of press lump system, there are 2 buildings in US that are underway. First one is the forestry building at the Oregon State University in Corvallis, Oregon, just an hour's drive south of Portland. It's a large educational building, 3 stories, post-tensioned walls, area about 8,000 square meters. The main designers are Equilibrium Consulting from Vancouver, and they've come up with a really good system. This is the picture that I took from the construction on April 17th, so not even a week old. As you can see, you have lots of walls, and all of these walls that you see, every single wall will be a post-tensioned wall. Post-tensioned rocking wall. Also some construction photos, again, post-tensioned walls. In this case, they basically didn't leave enough space between the UFPs in the wall, so basically they cut both sides of the wall to make enough space for the UFPs to fit in. And they also used another innovative solution. They put the UFPs in many places at the end of the wall. So this is the wall. This is a steel member that goes alongside the wall. So basically acts as a hold down. Let's put it a hold down at the end of the wall that goes all the way up towards the end of the wall. So basically you have kind of a hold down solution that has UFP on it. So this system, again, gives you different by having an experienced designer, of course, you can come up with the different solutions, and solutions that are really best fitted for the project. The second building will be much higher. It's called Framework Building. It will be in Portland, Oregon. 11-story, 43 meters high. This will be the tallest post-tensioned all-wood building. And actually, it will be the tallest all-wood building in the world when it's built, because the one in Vancouver that I showed you, it has concrete cores. This one uses all wood. You will hear a lot about this building because they had really tons of innovative ideas in these buildings, in this one. First of all, large spans. One of the problems for wood is having low stiffness. Is large spans are difficult. They managed to basically provide very large spans, and they've come up with lots of innovative details in respect to the post-tensioning system. The structural system is here. So we have the lateral system on the left. Again, lots of balloon shear walls all the way up, and cores for the elevators, and glulam columns and CLT floors taking the gravity load. Another detail here, energy dissipators. Again, here again they put the energy dissipators towards the end of the walls, not in the middle. Again, there is a reason for it, and that fitted their solution better. So finally, just a few words about another product called dowel laminated timber. It's a very old product. It's nothing new, probably it's been around 100 years, but it's been forgotten most of these 100. Now in Canada, basically Structurecraft, a company located just outside of Vancouver, they opened a new plant a couple months ago. And they can produce dowel laminated timber panels which are 3.7 meter wide to 18.5 meter long. Based on the demand, they can go even wider and longer. But this is for now what they can produce. Basically, how this system works is you have your dowels, wood dowels. You dry them almost as dry as possible. Then you enter them into the wood. So then the wood should be somewhere between 12% moisture content, while the dowel is around 5% or even 2% moisture content, if possible. Then what happens after the dowel is driven in, it sucks up the moisture from the lumber, the moisture during the equilibrium content from the lumber, and swells. By swelling, basically it locks the panel together. So it's been a concept that's been used for centuries, but not lately and not in applications that we see today. The company invested heavily into the new plant, and they really are seeing a lot of benefits, primarily using for floors. Of course, for walls it will be difficult, but for floor applications, it's a really good system. Finally, federal government of Canada just announced a few months ago that they will invest $40 million over the next 4 years for their new program called GC Wood, Green Construction Through Wood. This will to support, again, demonstration projects and activities related to use of wood, not only in tall buildings, but generally in infrastructure. So the first call for proposals went out, and we are in the process of reviewing now the proposals. 14 applications were received. Worth of the projects is about 880 millions. About 8 10 to 12 story buildings, 4 12 to 20 story buildings, and 1 20+ story building are in the competition. We will know in a few months which one will be chosen. We expect probably 5 buildings that will be sponsored by this program. And there will be a call next year for not only for tall buildings, but as I said, general for infrastructure. So even bridges, industrial buildings, anything that can really showcase wood into different applications. On the codes and standards activities, CLT has a product standard in North America called PRG 320. The first edition was in 2011. The latest one is this year, 2018. We just completed it. CLT is included in the 2016 CSA 86, which is the Canadian wood design standard. And included as a product with its bending, shear, stiffness properties and so on, but also connections. And also there's a part in there that basically tells us how to design CLT as a platform type lateral load resisting system, so used for wind loads or for earthquake loads. Mass timber will be allowed up to 12 stories in the 2020 National Building Code of Canada for gravity loads only, not for lateral loads. So we are in, from the fire perspective, so we are in an interesting situation right now in Canada because it was always us, the structural engineers, who were pumping our chest, if I can use that word, like we can build, no problem, but the fire was the obstacle. It was always the fire was the obstacle for wood. So now in the code, basically, fire is not obstacle up to 12 stories, but we don't have a system to go up to 12 stories, which is codified. We have, of course, alternative solutions, and I've showed you some, but we don't have a system for lateral loads that can go 12 stories. So first time in a long time, structural engineers were kind of behind. And in the United States, there is a proposal now in the International Building Code for use of wood up to 18 stories. And there's from what I'm hearing, lots of positive feedback on this one, so most probably this will go in. So by 2020, you will have 12 stories allowed for gravity loads in Canada and 18 stories in the United States. So finally, the research, all this research that I've shown helps really early adopters. I'm just going to show you some CLT buildings, not all of them tall, but in different applications. This is UBC Okanagan campus fitness center, very nice application, UBC CLT with LVL. This is the Center for Interactive Research on Sustainability at UBC in Vancouver. Beautiful building. If you had the chance to visit Vancouver, you have to visit UBC. We have more than 12 innovative wood buildings. This is the Earth Science building, again at UBC. Marvelous building, lots of innovative solution, including the stairway, a floating stairway out of wood with zero, you can jump on it, doesn't move. That was a huge marvel for the designer. The Energy Center, a massive CLT hall. There's lots of turbines here, lots of heat. So again, different application for CLT in a different building. Fort McMurray, it's a town in northern Alberta in Canada. This is the airport. It is still by area the largest building that uses CLT. 17,000 square meter building, still the largest by area building that uses CLT panels. And the Renaissance continues. Some of you might be familiar with this. This is the Tret building in Norway, completed a few years back. 14 stories, 51 meters. When completed, it was the tallest building in the world. Now the Vancouver one is the tallest, but Vancouver one will be overtaken soon. This is a building in Brisbane, Australia.